Hello everyone, today we're going to be going over the January 2025 English Language Arts or ELA Regents Exam. In this video, we're going to be focusing on Reading Comprehension Passage C from Part 1. Right, so if you didn't know, Part 1 is split up into 3 different passages. There's one passage about fiction, one poetry passage, and one nonfiction passage. So in this video, we're going to be going over the nonfiction passage from Part 1. So if you want the videos that go over the fiction and poem passage, guess what? They're going to be linked in the description of this video for you to check out as well. So that being said, we're going to go ahead and we're going to read this passage starting with the title. It says it's about beautiful brains, and it says, the first full series of scans of the developing adolescent brain, a National Institute of Health (NIH) project that studied over 100 young people as they grew up during the 1990s, showed that our brains undergo a massive reorganization between our 12th and 25th years. The brain doesn't actually grow in size very much during this period. It has already reached 90% of its full size by the time a person is 6, and a thickening skull accounts for most of the head growth afterwards. But as we move through adolescence, the brain undergoes an extensive remodeling, reassembling, and network and wiring upgrade. For starters, the brain's axons, the long nerve fibers that neurons use to send signals to other neurons, become gradually more insulated with the fatty substance called myelin, the brain's white matter, eventually boosting the axon's transmission speed up to 100 times. Meanwhile, dendrites, the branch-like extensions that neurons use to receive signals from nearby axons, grow twiggier, and the most heavily used synapses, the little chemical junctures across which axons and dendrites pass notes, grow richer and stronger. At the same time, synapses that see little use begin to wither, and if you're withering away, that means you're decreasing in size. This synaptic pruning, as it's called, causes the brain's cortex, which is the outer layer of gray matter where we do much of our conscious and complicated thinking, to become thinner but more efficient. Taken together, these changes make the entire brain a much faster and more sophisticated organ. Okay, so essentially what this says is your brain develops extremely importantly, right? It undergoes an important change between your 12th and 25th birthday, right? Through this time, it's not like your brain is actually increasing in size, but it's remodeling itself, all right? So it's myelinating its fibers, it's making its dendrites grow twiggier, right? It's making its synapses grow richer and stronger, and at the same time, it's using these useless connections and it's degrading them, right? And it's ultimately making your frontal cortex more efficient. Okay, so that's what this first part says. All it's saying is that you get a wiring upgrade. It gives examples as to what specifically that wiring upgrade is in terms of neuroscience, like myelin, dendrites, etc., using that like official science vocabulary. And then finally, it says that the effect of this is that your brain runs more efficiently. Okay, this process of maturation, once thought largely to be finished by elementary school, continues through adolescence. Imaging work done since the 1990s shows that these physical changes move in a slow wave from the brain's rear to its front, from areas close to the brainstem that look after older and more behaviorally basic functions, such as vision, movement, and fundamental processing, to the evolutionarily newer and more complicated thinking areas up front. The corpus callosum, which connects the brain's left and right hemispheres and carries traffic essential to many advanced brain functions, steadily thickens. Stronger links develop between the hippocampus, a sort of memory directory, and frontal areas that set goals and weigh different agendas. As a result, we get better at integrating memory and experience into our decisions. At the same time, the frontal areas develop greater speed and richer connections, allowing us to generate and weigh far more variables in agenda than before. So this is again implementing or giving you even more details on how exactly our brains become more efficient as they develop, right? And more specifically, it tells us how we actually develop. It goes in a wave-like fashion. So it goes from the back of your head or the back of your brain to the front of your brain. And as it's going to the front of your brain, that's the more complicated part of it. That's the one that's evolutionarily newer, right? That's what makes humans more unique than other animals, that specific front part of our brain. And as a result, as that front part of our brain develops more, we get better at higher order functions, right? We get better at, planning, at setting agendas, at implementing agendas. We're getting better at memorizing and integrating things into our memory, so on and so forth, right? So then it continues. When this development proceeds normally, we get better at balancing impulse, desire, goals, self-interest, rules, ethic, and even altruism, which is a concern for others. So you ultimately become a better person, kind of. Generating behavior that is more complex and is sometimes more sensible. But at times, and especially at first, the brain does not the brain does this work clumsily. It's hard to get all those new cogs to mesh. Okay, so at the end of this development, right, you become a much clearer thinker, right? You're better at balancing your impulses and your desires. You're better at you're better at having a concern for others and for rules. But the issue here is that even though you end up, a person who can think a lot better, the way that this upgrade happens isn't really coordinated. It's a clumsy change, okay, because it's a very difficult change. So this is now introducing an issue, right? Beatriz Luna, a University of Pittsburgh professor of psychiatry who uses neuroimaging to study the teen brain, used a simple test that illustrates this learning curve, right? So what is a learning curve? Well, it's just a curve that or it's a word that we use to describe how difficult it is to learn something or for some change to stick to you. So if this change in rewiring your brain is done clumsily, that means it's a high learning curve because it's difficult to do so, right? There's challenges that come from it. Luna scanned the brains of children, teens, and 20-somethings while they performed an anti-saccade task, a sort of eyes-only video game where you have to stop yourself from looking at a suddenly appearing light. You view a screen on which the red crosshairs at a center occasionally disappear just as light flickers elsewhere on the screen. Your instructions are to not move at the light and instead to look in the opposite direction. A sensor detects eye movement. It's a tough assignment since flickering lights naturally draw our attention. To succeed, you must override both a normal impulse to attend to new information and curiosity about something forbidden. Brain geeks call this a response inhibition. So in this case, this is a perfect test to see the development of the brain simply because it tests how good you are at controlling impulse and following instructions, which again are some of the two things that your brain gets better as it develops. Okay, and they ran this test with people that were not teens, right? So preteens, with teenagers, and then with 20-year-olds. All right. So then it says that 10-year-olds stink at it, failing about 45% of the time. Teens do much better. In fact, by age 15, they could score as well as adults if they're motivated, resisting temptation about 70 to 80% of the time. What Luna found most interesting, however, was not those scores. It was that the brain scans she took while people took the test. Compared with adults, teens tended to make less use of brain regions that monitor performance, spot errors, plan, and stay focused, areas that adults seem to bring online automatically. This let adults use a variety of brain resources and better resist temptation, while the teens used those areas less often and more readily gave into the impulse to look at the flickering light, just like they're more likely to move away from the road to receive a text message, or look away from the road to receive a text message. So again, we're seeing a big difference between adults and teens, right? Between 10-year-olds who aren't teenagers, they really suck at this task, right? Because their brain hasn't even begun to be rewired. But with the teens, you can see that their brains are partially rewired because they do a lot better than 10-year-olds, but still they lack some of that activation that adults have. Those adults have a fully developed brain. Right, so then it says if offered an extra reward, however, teens show that they could push those executive regions to work harder, improving their scores. And by age 20, their brains responded to this task much as the adults do. Luna suspected that the improvements come as richer networks and faster connections make the executive regions more effective. These studies help explain why teens behave in such vexing inconsistency. Begulling, which means charming, at breakfast, disgusting at dinner. Masterful on Monday, sleepwalking on Saturday. Along with lacking experience generally, they're still learning to use their brains' new networks. Stress, fatigue, or challenges can cause a misfire. Abigail Baird, a Vassar psychologist who studies teens, calls this neural gawkiness an equivalent to the physical awkwardness teens sometimes display while mastering their growing bodies, right? So they're saying that this clumsy remodeling of the brain is supposed to explain how teenagers act, which I think is a little bit stupid, like to put it this way. But again, they're pretty much saying that, well, it's a messy project and process to reorganize how your brain is. So it's much like how awkward it is to get used to your new body as you're growing as a teenager. All right. The slow and uneven developmental arc revealed by these imaging studies offers a alluring, pithy explanation, right? Pithy means concise, right? So an alluringly concise or, very detailed and straightforward explanation for why teens may do stupid things, like drive at 113 miles an hour, aggrieve their ancestry, which is your elderly, and get people or get gotten with child, which means get pregnant. They act that way because their brains aren't done. You can see it right here in the scans. So they're saying why teenagers are so impulsive or moody is because their brains haven't been developed. No offense. Right? So it then says, meanwhile, in times of doubt, take inspiration in one last distinction of the teen brain, a final key to both its clumsiness and its remarkable adaptability. This is the prolonged plasticity of those late developing frontal areas as they slowly mature. As noted earlier, these areas are the last to lay down the fatty myelinated insulation, the brain's white matter, that speeds transmissions. And at a first glance, this seems like bad news. If we need those areas for complex tasks of entering the world, why aren't they running at full speed when the challenges are most daunting? The answer is that the speed comes at the price of flexibility. So it's saying that plasticity and flexibility are kind of the same thing. While a myelin coating greatly accelerates an axon's bandwidth, it also inhibits the growth of new branches from the axon. According to Douglas Fields, an NIH neuroscientist who spent years studying myelin, this makes the period when a brain area lays down a myelin a sort of crucial period of learning. The wiring is getting upgraded, but once it's done, it's hard to change. The window in which experience can best rewire those connections is highly specific to each brain area. Thus, the brain's language center acquires their insulation most heavily in the first 13 years, when a child is learning language. The completed insulation consolidates those gains, but makes further gains, such as a second language, far harder to come by. So it is with the forebrain's myelination during the late teens and early 20s. This delayed completion, which is a withholding of readiness, heightens the flexibility just as we confront and enter the world that we will face as adults. Right, so this is saying that one unique thing about the teen brain, right? It's not all bad being a teenager because even though your brain's underdeveloped, it's very plastic, right? It's very flexible, and it's a unique thing, right? This is a very unique thing or part of your brain, the fact that it is so flexible, the fact that it can change so quickly. Right? Why? Well, because when you fully upgrade the wiring, it's hard to change the connections that are already been made, right? So a reason why the teenage brain takes so long to develop, why it spans from late elementary school or early middle school all the way until or from whenever you're 13 to 25, why it takes literally 12 years for your brain to fully develop, is because if it immediately developed, it wouldn't be able to form necessary connections, right? It would be less plastic and less malleable. Right. So then finally the conclusion says this long, slow back to front developmental wave, completed only in the mid-20s, appears to be a uniquely human adaptation. It may be one of our most consequential. It can seem a bit crazy that we humans don't wise up a bit earlier in life, but if we smartened up sooner, we'd end up dumber. All right. So again, this entire passage just talked about brain development, okay? Specifically how uniquely the human brain develops between the ages of 13 and 25. That was pretty much it, right? They talked about what those upgrades were. Your brain gets myelinated, your connections get myelinated, your dendrites become more twiggy or branchy, and your synapses become a lot richer, okay? And as a result, you get higher, you acquire a better, higher order functioning, right? You're able to function better. You're able to make better decisions. You're able to weigh, pros and cons better. You're able to be, more compassionate towards others. And the way that we prove this is through one of these experiments where they gave teens, preteens, and adults kind of this video game with the flashing light that they had to avoid. And what they saw was, again, adults were better at making those higher order decisions than teens simply because their brains were more developed. And the reason why this development doesn't occur immediately is because the brain needs plasticity. If the brain gets myelinated or upgraded too quickly, it's not plastic, it's not as malleable or as changeable or as flexible, and as a result, like they say down here, it says we may end up stupider if we don't have that kind of time period where our brain is rapidly changing, right? Or that time period where our brain is so flexible. All right, so again, they use this to kind of explain why teenagers are the way they are, and that's pretty much the main point of this text. All right, so we're going to go ahead and start off with number 15. It says the line or the metaphor in line 6 and 7 serves to do what? So let's go ahead and let's read lines 6 through 7. If you're confused about this formatting, that means that the line itself starts with but as we, and it ends with wiring upgrade. All right, so let's go ahead, let's look at this. So 6 through 7, and it says right here, it starts with but as So it says, but as we move through adolescence, the brain undergoes an extensive remodeling, reassembling, a network, and a wiring upgrade. All right. So what's happening here is that they're using this metaphor, right? They're comparing our brain development to upgrading a computer's wires. Why do they do that? Well, it's probably to make the language less complex and to kind of break down or boil down this complex, topic of neuroscience into something that, regular high schoolers can understand while they're taking the Regents. Okay? So let's look at what choice says that. Right, so if we look at through these choices, obviously it's going to be 4, right? It's to link a simple and complex ideas, right? The complex idea is how brains develop, right? That's something that, neuroscientists have to discover. But, a simpler idea is, oh, I'm just replacing the wires, right? If we think about our brain as a collection of wires, well, the developing brain is just replacing those old wires with newer ones and ones that are more faster. Okay, so comparing our brain to, a collection of wires, again, links a simple idea we're developing with a complex idea that our brains are changing in some sort of way, right? There's no ironic tone here, at least not in the first paragraph, okay? There's no irony here, there's no contradictions. There's no prior and current knowledge, right? Because we didn't come into this exam with any prior knowledge of whatever this text was going to be about. And again, there's no hypothesis in just saying that our brain develops. All right, number 16 says the goal of synaptic pruning in lines 14 through 15 is to alter the brain cortex's productivity, right? It says synaptic pruning was talked about up here. It says that as at the same time, synapses that see little use begin to wither. This synaptic pruning it causes the brain's cortex, the outer layer of gray matter where we do much of our conscious and complicated thinking, to become thinner but more efficient. All right, so this pruning, it literally said that this pruning causes our brain to become more efficient, right? So if you're more efficient, you're more productive. So this pruning has to increase productivity, and that should make sense, right? If your brain is a collection of wires and you get rid of wires that don't really lead anywhere, you save up more space for more important wires to take up that position or that old space. All right, pigment is colored. There's nothing, no mention about color in this entire passage, I guess, except for in the experiment, right? This has nothing to do with protection. That's your skull. And position, again, your brain isn't changing its own position. What's happening is it's changing its productivity. Number 17 says the purpose or the primary purpose of lines 19 and 20 is to do what? Right, so go ahead and let's read lines 19 and 20. So it says this process of maturation, once thought to be largely finished by elementary school, continues through adolescence. Imaging work done since the 1990s shows that these physical changes move in a slow wave from the brain's rear to its front. All right, so lines 19 through 20 are these first two lines, and what it shows or poses is a contradiction, right? Before we actually talk about how the brain itself is going to develop, what we need to first introduce is how this is a relatively new idea, right? Because up until now, we thought that the process of maturation only finished by elementary school. Now we know that it doesn't, right? It goes on for a much longer period of time throughout adolescence. So what 19 through 20 do is they introduce a topic by predicting or by noting a misconception, all right? That's a misconception, right? What is a misconception? It's something that has been proven to be false that people thought to be true, all right? So choice 1, if we read up here, again, 19 through 20, it was once thought. If something was once thought to be something, we don't think it anymore. We think about it differently now, right? Remember, once, not anymore. Okay, so again, that has to be a misconception because we now proved it to be wrong. It's not predicting a problem. It's saying that, oh, there was a problem in how we used to think about brain development. This is the better way of thinking about it. Again, this is not an opinion. This is an article, right? This isn't someone's opinion. This is, definitive facts about how the brain is going to develop. And again, there's no real argument here. No one's arguing for or against the point. This is kind of showing the findings of many years of research in this case. Right, number 18 says the description of the brain's development in lines 19 through 30 implies that the brain matures how? Or as the brain matures, is memory adversely affected? No, I remember reading in it saying that memory was actually increased, right? Or your memory ability or memory capacity went up or got better. All right, and I'm sure that if I look back at lines 19 through 30, I can prove that to you. All right, we get better at integrating memory. Guess what? If you're integrating memory, that means you're memorizing things better. So as a result, you do not get worse. If something is adversely affected, that means it's negatively affected. Adversity is something that's bad. So if you adversely impact something, you're negatively impacting it. Choice 2 says that as the brain matures, its process speed is compromised. Well, if something is compromised, that means that it has to give something up, right? Or something loses something, right? If the processing speed is compromised, that means that we're losing the processing speed. But remember, the whole point of this article is to show that as the brain develops, you get faster and better at thinking. So obviously choice 2 is not the correct answer here. Choice 3 says decision making is greatly enhanced, and that's going to be the correct answer here. If there's one thing that you want to take away from this article is that as you get older and as your brain develops, it's better at decision making, right? It's better at making agendas, it's better at being more compassionate, it's better at reasoning and being more logical. And again, you can prove that through lines 19 through 30, right? If you're getting better at integrating memory, and at the same time the frontal areas get richer connection and allow us to generate and weigh far more variables and agendas than before, guess what? You're thinking at a higher level now. All right, number 19 says lines 31 through 34, when this development to does this work clumsily implies that the process of normal maturation is what? Well, hold on. Before we read this, we can just answer this from here, right? It's the line that says that it's describing the development as clumsily. So if something is done clumsily, that means that it has to be intricate and inconsistent, right? If something is done clumsily, it means that it's done inconsistently. If you're clumsy with your work, if you're clumsy in general, you tend to drop a lot of things, right? You tend to make a mess. Okay, so if you're a messy person or if a process is super messy, that means that it's not consistent, all right? So I'm going to predict that the answer choice is 4, and I know that the answer choice is 4, but let's read lines 31 through 34 again, all right? So it says, when this development proceeds normally, we get better at balancing impulse, desire, goals, self-interest, rules, ethics, and even altruism, generating behavior that is more complex and sometimes at least more sensible. But at times, especially at first, the brain does this work clumsily. It's hard to get all those cogs to mesh. So if it's hard to get all those cogs to mesh, that means that it's hard to do it all at the same time. And as a result, if you're clumsy, you're uncoordinated, right? And it's inconsistent. So the process itself is intricate, right? To be intricate is to be complex, right? Developing a brain and maturing a brain is a very complex process. The text for sure stated that. But it also stated that it was done clumsily, and as a result, teens are more impulsive, and less stable for that reason, which is where the inconsistency comes in here. Right? If the development was uniform and predictable, we wouldn't describe it as clumsy. If it was immeasurable and mysterious, then we wouldn't have an article talking about how the brain literally develops. And if it was unchangeable, then the brain would never actually develop, right? And if it was instant, well, this whole article wouldn't talk about how the adolescent brain develops until it's 25, right? This article wouldn't exist if our brain instantly developed, because the whole thing that this article is driving home, the whole point that we're driving home here is that the brain develops between your 13th and 25th birthday, and it changes drastically. Right? Number 20 says lines 51 through 53 contribute to the effectiveness of the text by doing what? So let's look at 51 and 53. So here we have 51. It says, this lets the adults use a variety of brain resources and better resist temptation, while the teens use those areas less often and more readily gave in to the impulse to look at the flickering light, just as they're more likely to look away from the road to read a text message. So again, this is a part of the paragraph that's talking about the results of the test, right? It's saying that teens were worse at taking the test than adults because they had worse impulse control because, again, their brains weren't fully developed at this time. So these lines, which literally state what I just said, the fact that teens are worse at doing these, that it's talking about proof, right? The specific proof of how teens are doing worse on these cognitive tests than adults show what? And obviously they show a familiar, or they're presenting a familiar example, right? Again, we just stated how teens were worse off at using that part of the brain that hasn't yet been developed, right? That part of the brain that controls impulses. And we're presenting an example of how teens again, are bad at controlling impulse, right? The example is that, well, because their brain isn't developed, as a result, they will, pay attention to the colors, right, in the flashing light instead of looking away. And again, they showed another example. Oh, well, just like a teen is more likely to be distracted while they drive, right? Why? Because they don't have as much impulse control. So both the comparison to the kid driving the car, if this was 51 through 53, right here, right, the impulse to look at a flickering light and the impulse to look away from the road to read a text message, again, these bring up a familiar example of how teens have less impulse control. And if you want to look at the words that are in between them, right, or all three of these sentences as one, it's giving an example of how teens' brains develop slower than adult brains. Right? So number 21 says, as used in lines 54 and 55, the term executive regions most likely refers to the brain area that does what? Well, obviously, it's the one that's going to control responses, right? The executive region of the brain is the one that's going to control your impulse, right? The impulse control, right? 51 and 54 and 55 is talking about how teens have worse impulse control because of the worse executive function. So the executive part of your brain has to be the one that controls impulses if that's the part of your brain that, or if that's the part of the brain that shows that big difference in development between teens and adults. Right, number 22 says, as used in the text, the word plasticity in line 70 refers to the brain's ability to do what? So let's look at line 70. Right, it says that the plasticity of those late developing frontal areas as they slowly mature. Right, so let's read the full sentence, I guess. This says that this is the prolonged plasticity of those late developing frontal areas as they slowly mature. As noted earlier, these areas of the brain are the last to lay down the fatty myelin insulation, the brain's white matter, that speeds transmissions. At a first glance, this seems like bad news. If we need these areas for the complex tasks of entering the world, why aren't they running at full speed when the challenges are most daunting? The answer is that speed comes at the price of flexibility. So what this part of the text just told us was that the brain, as it's being myelinated and developed as you're growing older, loses its flexibility. All right, it loses its plasticity, and as it's and then the article brings up a good question, right? It's like, well, why would we slow down that myelination if we want our brain to be more complex? And they say that the reason behind that is because it comes at the price of flexibility. So teens have high plasticity, meaning that they have high flexibility. So these two words come hand in hand. And if something is really flexible, well, guess what? It's able to change a lot, right? If something is plastic, right, as opposed to metal, it's less rigid. You can change the shape of it a lot more. So calling a brain plastic and flexible shows not its reluctance to accept directions, not its ability to make distinction, but its capacity to undergo modification, right? If something is super flexible, right, if you have flexible plans, guess what? Your plan, you can change, right? If you have a flexible schedule, you can change your schedule, right? AKA you can undergo a modification. So number 23 says lines 88 and 90 provide information that is what? So let's go ahead and let's read 88 and 90. So here's 88. It says that it may be one of our most consequential. It can seem a bit crazy that we humans don't wise up a bit earlier in life, but if we smartened up sooner, we'd end up dumber. So it's saying that, against all expectations, right? Seemingly counterintuitively, if we developed our brain super quickly, we would have lost a lot of its good functions, right? So lines 88 through 90 provide information that is contrary to expectations, right? If something seems a bit crazy, that means that it's against your expectations. You don't expect that thing to happen, or you're not expecting that to be a real thing, right? Think about if your friend told you something that was like kind of outrageous, you'd say, no, that's crazy. Why? Because you weren't expecting that. Okay, so the fact that they're calling it, the fact that our brain doesn't develop very quickly crazy shows that it's against expectations. And finally, 24 asks us which statement best identifies the main effect of the myelinating process. And again, it's talking about the speed, right? The myelination is whenever you coat these brain cells with this fat or this white matter, and that speeds up its transmission. All right, so choice 1 can't be correct because it's talking about a thickening skull. Myelin has nothing to do with how thick the skull is. Choice 2 is wrong because myelin has nothing to do with the synapses, right? And especially this pruning that they're describing here. This myelin has nothing to do with the fact that the synapses are going to wither away. All right, number 3 is wrong because a sensor has nothing to do with the main effect of myelination. Myelination has nothing to do with the sensor detecting eye movement, right? That's outside of your body. Myelination is inside of your body. What myelination does, however, is it coats your brain cells or those fibers with fat that then increase the transmission speed across it, right? It lets your wires or your brain cells fire their synapses or their signals at greater speeds, right? And a drawback to that greater speed is a reduction in flexibility. So the main effect of the myelination process is that it speeds up the communication, but it comes at the price of flexibility because it's harder to change when it's been modified. So that's the end of this section, and that's the end of part 1. So I've already uploaded the videos going over the fiction passage, the poem passage, and then this one was the review of the non-fiction passage. So, personally, this is my least favorite one because, it's just full of text and it's complex. But if you take notes, if you, step by step take breaks in the middle of your reading to kind of talk to yourself about, well, what the hell did I just read? You'll find it easy and you guys will have a good time on the Regents, okay? So if you have any questions, please feel free to let me know in the comments. Please check out the other videos that I've uploaded on this test, and if you need other Regents help, please check out the videos I uploaded on just other Regents topics. Hope you guys learned something, and I hope you have a nice night.